Hello, everybody, and today's lecture is on implicit differentiation, the implicit derivative. So, what are we talking about here? If we have an expression like x squared plus 3xy minus 4 equal to 0, and I want to at the point 1 comma 1 find dy dx, how would I do that? So why is this called implicit differentiation? The answer is because we don't have it in function notation. That is, there's no function here. This is an equation. We have f of x equals x squared plus 2. That would be an equation. That would be an explicit equation. This is an implicit equation right here because it is not solved for y, it is not solved for x, and so it's implicitly defined. So how does one take the derivative of this? Well, this is what you do. First thing you do is you have to understand what this says. This is the derivative of y with respect to x. This is going to be extremely important when you do implicit derivatives. So over here, what I do is I take the derivative using the rules I know. That is, the derivative of x squared should be 2x. And it is. Now, because this is x, the variable that's in the denominator, that is the variable with respect to, I call it the good variable, the variable that does not need an extra chain rule because x squared is the variable of with respect to. Plus, now we're already jumping into a very slightly complicated problem because we actually have x and y multiplied. And what's causing an issue here is the fact that we have a y that could be some kind of function, but we just decided to use y instead of the function name. So I'm really imagining right here y is some nasty, ugly function, and we're just calling it y to make our shorthand easier to read. So because it's 3x times another function, that means I have to use a product rule. So as a shortcut to understand, when I have back-to-back variables, when we're doing implicit derivatives, it'll always be a product rule. So that means, yep, you guessed it, product rule time. So what's the product rule? Well, it is u prime v plus u v prime. And I'll fill those in. Let me continue on. This is a product rule. Let me continue on. At this minus, we'll take the derivative of this. Well, that's 0, so that disappears. Equals. And when you take the derivative of one side, you also have to take the derivative of both sides. It kind of keeps the scales balanced. You can't do the derivative on one side and not the other. So we take the derivative on both sides. So the derivative of 0, well, that's easy. It's a constant. The derivative of 0 is 0. Back to the product rule. So how do we take the derivative via the product rule? You need your u. Let me highlight my u. There's my u. And then I need my v. My v, I'll highlight in green. There's my v. So I have my u and my v. So it is u prime, derivative of 3x, which is 3. Did not know that. Which is 3. Leave this alone, right? It's u prime v, plus u, well, 3x. Now here comes the interesting piece. The derivative of y, well, it should be 1, like we know and love. But because that is a y, and that is the top letter, it's kind of like a function. So it's kind of like a chain rule. And that's really what I'm looking at is a chain rule. The derivative of y should be 1, but what's inside of y? What is the function inside of y? I don't know it, so I'm going to write it as y prime. That's all I can write it is y prime. I don't know what the derivative is, but I'm going to call it y prime. By the way, dy dx and y prime mean the exact same thing. It's just a shorthand symbol as I've taught you. All right, so we have this long expression that I just took the derivative of. I want y prime because it says find y prime, right? dy dx, find y prime. So I'm going to now simplify. Okay, it's good algebra. 3 times y is 3y. 3x times 1y prime is 3xy prime. You would just smush all these together because that's proper algebra, proper multiplication. We're going to be using a lot of algebra when we do implicit derivatives. So there is my expression a little bit simplified. So we're always going to use the same rules of algebra now. That is, I want to solve for y prime. So the terms that do not have y prime, right here, I'm going to always first subtract them over, move them to the other side. See, this term has a y prime in it. I want to keep it on the left side. I want to move these terms over so they're on the right-hand side of the equation. When I do that, when you move things across to equals, you have to change your signs. So the opposite of 2x is a negative 2x. The opposite of 3y is a negative 3y. And last but not least, if I want to solve for y prime, I'm going to divide both sides by the item in front of the y prime, the multiplier in front of the y prime, which is the 3x. So my y prime is actually negative 2x minus 3y, that's my numerator, all over 3x when I solve this expression. So there is my derivative formula. Now when I look at this, I see it's very complicated. Please, you cannot cancel the x's. That's bad algebra. That minus here links these two terms forever. So there is really no reduction in this expression. Now let's go back to the question to make sure we answered it. It says, for this equation, I want to find dy dx. I did that. Oh, but I want to find dy dx at the point 1, 1. So the last thing I need to do is to plug in the point 1, 1. So here we go. We plug in 1 for x, and just understand, the first one is for x, the second one is for y. Know what you're evaluating, know what you're plugging in. All right, now we simplify. Negative 2 minus 3 is a negative 5, and 3 times 1 is a 3. And so that is my final answer. The derivative is negative 5 over 3. What does that mean? Well, as you recall, the derivative is the slope, or in this case, I'm going to get away from the definition of slope in this case, even though it is slope, because dy dx is always a slope. Change in y over change in x, right? That's always a slope. I want to look at it more of a rate of change. What this is telling me is, let me write it, as I increase x by 1 unit, so whatever's going on with x, so as I increase x by 1 unit, it says the denominator, as I increase x by 1 unit, the change in y will be estimated by this. Then, in this case, I'm going to have to say decrease because it's negative, then the y decreases by 5/3. Because of this negative, it tells me my rate of change is decreasing. So as I increase the x by 1 unit, and whatever x stands for, it could be units, could be time, whatever x stands for, as we increase by 1 unit, this is what's happening to the y, whatever the y stands for. So then the y will decrease by 5/3 of a unit, so just under 2 units. And that's our answer. Let's look at another problem, and let's bring in some exponentials just so we can review that. Let's say we have the expression x e to the y equals 2y plus 3, and I want to find, once again, dy dx at the point 3, 0. Okay, so because it's dy dx, I can once again say I'm finding the slope. Or in this case, you could say, I want to find how will y change with respect to x? That is, as x changes 1 unit, as we change x 1 unit, what happens to the y value? And that's really what I want to know at this point. I'm at this point 3, 0. What happens if I make a little change? Let's investigate. Well, to take the derivative implicitly, again, why is this implicit? Because it's not y equals. You cannot solve this elegantly for y equals. And that's why it's an implicit equation. That's no big deal. We have rules for implicit derivatives. How do we do it? Well, we take the derivative of the left side, we take the derivative of the right side, and we set them equal. So the derivative of the left side, well, once again, my friends, when you have back-to-back variables in an implicit equation, you're going to use the product rule here. So this is definitely a product rule. So once again, setting up my brackets for the product rule. And now let me take care of the right-hand side because it's easier. So on the right-hand side, I have a linear piece. I'm going to take the derivative of this and the derivative of this and put it together. The derivative of 3, well, that's easy. That's 0. The derivative of 2y, here we go again. Let's do a shortcut. It's the top letter. The y is the top letter. That means y is the function. Y is the function we don't know. So first, we take the derivative like we think. The derivative of 2y. The way I look at it is, I take the derivative of 2y like I should. It's 2. But I look to see if this letter matches the numerator letter of my derivative. And it does, so that means I have to do the chain rule and multiply by y prime, whatever the inside of y is, which I don't know, and that's why we write y prime. All right, let's get to the left side. We have to do the product rule. So on the left side, we have derivative of x, no big deal. That's 1. Leave the second piece alone, plus x, leave the first alone. Now I got to take the derivative of the second piece. With the derivative of the exponential, as you review my videos, the derivative of the exponential is e to the y times the derivative of the exponent. And the derivative of y, well, again, we don't know what it is, so we're going to call it y prime. All right, and because I'm short on time, I have to quickly now solve this for y prime. Left-hand term simplifies pretty easily. The right-hand term, same thing. I just put them all together. Now in this, I see I have a y prime on two opposite sides. So I'm going to try to get the y primes on the same side by moving this term over to the right by subtraction. So I leave the e to the y this time by itself, and I move the x, e, y prime by subtraction, because how do you get rid of a plus? The opposite operation would be a minus, and there you have. Now both of these terms have a y prime. What that means is I can factor out a y prime on this side. So I get 2 minus x e to the y when I factor out the y prime. Now that the y prime is factored, I can divide this parentheses over, and my expression, very complicated, though it's done, is e to the y in the top, and then divide over the 2 minus x e to the y for my denominator. That is a minus. And so that is my derivative. I still have to go back up top and plug in the point 3, 0 to be done. Because it did say find, that's a so find the derivative at the point 3, 0. So wherever there's an x, I'm going to plug in a 3. Wherever there's a y, I'm going to plug in a 0. So wherever there's an x, I'm plugging in a 3. Wherever there's a y, I'm plugging in 0. And whatever number this is my answer. Top is 1 because e to the 0 is 1, and the bottom's negative 1. And there's my rate of change. It's the 1 to a negative 1 rate of change. Thank you for watching the first video on implicit derivatives.